Okay, let's discuss. Let us discuss and see.
Yes, sir. Sir, first we will discuss with week 2. Can you? Hello, sir.
You can see the screen, right?
Sir, week 2, question number 1.
Is this one or the earlier one? Hello. Hi.
Yes, sir. Hello, sir.
Oh, okay.
Can you hear me, sir?
Yes, I can hear you.
Sir, week 2, question number 1. This is a question. Consider the hash family of H1, H2, 1 to 3 goes to 0 and 1. Okay, sir? Is the hash family universal? So the solution is also given, sir. H of x equal to h of y equal to 1 by 2. How, sir, and why, sir?
So it is saying that we need the probability to be half, but it is not.
Yes, sir.
Because you see that at bit so when it is 1, so for the value of 1, h1 takes 0 and h1, so h1 is 0 and h2 is 1, and that's exactly the same as the position at 3. So the probability is 1. So if h1 is 0, then here for 3 also it's 0. So they exactly match.
Okay.
That's why it's
And the
saying that
probability is 1.
since the probability is 1, therefore it's a violation. So they should not have matched.
Yes, sir.
Yeah, okay.
Sir, suppose there are 4 elements and there are 3 hashes. 1, 2, 3, 4 and H1, H2, H3. Then what would be the universal formula for hash family H?
So you have H1, H2, H3.
H3, H4.
Okay, you have H1, H2, H3, H4. And how many elements are you saying?
Suppose 5 elements are there.
Okay. 5.
How I will do? I will do according to half only, 1 by 2. That is the formula.
So since there are only since there are only 2 positions, all right, and each, so basically there is 5. So there are 5 hash functions and there are 2 possibilities for each element.
Okay.
So then you have to see that there is someone. Okay. So to clarify, let us look at the slides once.
Yes.
So this, oh, sorry. So what you want is for to define a good hash function, you want it to be uniform in its mapping. So it has equal probability to, so regardless of, so what they say that, regardless of the, so if any hash function, regardless of the target I, should have a uniform probability of mapping. That is not good enough. Why? Because let's say, so basically you can have 2 hash functions which all do the same mapping, and then there is no then there is basically duplicacy. So basically you want each function of your hash family to map the elements in such a way that the probability of collision is 1 by m.
Yes, sir.
Okay, so basically, for example, in this thing, you have you always have a collision between, so the probability of H1 mapping 1 and 3. So the H1 maps 1 and 3 to the same position, and H2 also maps 1 and 3 to the same position.
Yes, sir.
And so you see that there is like one probability of collision. So you don't want that to happen.
But sir, what I'm saying that from the can you please get the question, sir?
Oh, okay.
Sir, this 0, 1, 0, 1, 0, 1, 0, 1. What is 0 and 1? These are positions, no?
These are the, you can think of them in the position. So let's say you have a target table with 0 entry and 1 entry. So it's one of those positions, let's say.
Okay.
That is one way to
H0
think of it.
at 1 is at 0 and H2 at 1 is at 1. So there is no collision, no, sir. Position is different, 0 and 1.
No, because your H1 maps 1 to 0 and 3 to 0.
Okay.
Right. So there is a collision there. And H2 is mapping 1 to 1 and 3 to 1. And there is always a collision there. So, you know, both H1 and H2 always have a collision in 1 and 3. That's the problem. There is no hash function here which does not have a collision between 1 and 3.
Okay.
Right.
Take 1 by 2. This is the universal formula.
So the formula, like for your question, your M is known. So what is M here? M is the number of basically target positions, right? So M is, so here's the constraint. So we have 0 and 1, so our M is 2. If we have 0, 1, 2, 3, 4, 5, our M is 5, right?
Okay.
That's the target position. On the left hand side is your universe of inputs. It can be as large as possible. Usually M is far smaller than the universe.
Yes, sir.
So number of target positions is far smaller than the number of elements you are mapping. So here in the formula, we have to put 1 by M here. So 1 by M is the number of target positions. Sorry, this is the uniform thing. We are looking at the universal thing. So here you have to put the one. Let's say you had in your alternative example, you had 5 items. So you will put 1 by 5 there, and you will compute the probability for any X and Y. You know, what is the probability of this M?
So
collision.
Every time it will be 1 by 5 only. There are 5 ways.
Yeah, it's supposed to be for universal.
Okay. One more question, sir. Question number 2. I think this is wrong. Question number 2.
Okay. Let's read it. Suppose a Bloom filter is constructed with 3 hash functions, that the bit vector is this. Now, for a query element, if the hash values are 6, 2, and 3, what can be said about element X?
Sir, what I did, can I say something? What I did, I made an array of 8 elements, 0 to 7, okay? And I put all these bits, 0, 1, 1, 0, 1, 1, 0, 1, okay, sir? Now what I'm doing, H1 of X. H1 of X equals to 6, H1. So H1 of X will 0, 1. H1 of X equals to 6, so we are seeing 1 over here. Is it okay?
Okay, yes.
H2 of X equal to 2. This is also 1 over here. Is it clear? H3 of X, this is 0 over here. Can you see the bit position?
Wait, it's 1 based indexing. That means that, okay, so 1, 2, 3, 4, 5, 6. So 6 is 1, that we agree. 6 is 1, right?
Yes, sir.
Okay. So
H2, X is 2, that is also 1.
Yeah. And H3 is 5. 1, 2, 3, 4, 5. Y is 0?
Sir, see. 0 position is 0 hai. First position is first, second position is second, third position is 0 hai. Can you?
Yeah.
Okay, sir.
No, basically, okay. So why were you saying H1 is 1? Because H1 is 6, but you are saying it gets a value of 1. Why would you say that? Explain the logic.
Because sir, I am putting this whole bit in an array. Okay. And then I am saying 0th position is 0, first position is first. Can you see?
No. So basically, 1-based indexing means you start counting from 1.
Okay, this is 1. This is 1.
Yeah. So you start not 0, 1, 2, 3, but 1, 2, 3, 4.
Okay. First position is 0. Is it okay?
First position is 0. Yes, you're right. Yes.
Each one of x equal to 6. This is 0. The value is 0. Okay.
H1 of x is 6. So H1 maps to the 6th position. What's the value in the 6th position?
Okay, H1 of x equal to 6 then?
So let's review the slides once again. So let's look at it. That's the correct. Let's see. So we are looking at Bloom filters, right?
Yeah.
Okay. So here's the hash code. So what's it's doing? You have this input x, right?
Yeah.
And you have H1 and H2 and H3, let's say, like in the example. So here you see H1 is mapping to a position. H2 is mapping to a position. H3 is mapping to a position. So, sorry, yeah. So let me just say this. So here, when H1 is, you are telling that H1 is equal to 6. That means that it's mapping to the position 6. And what is the value there? It's looking for occurrence or non-occurrence, 0 or 1. Sorry, occurrence is 1 and non-occurrence is 0. So at the 6th position, it's finding 1, 2, 3, 4, 5, 6, which is 1. That means there seems to be an occurrence, right? Is the logic clear?
1, 2, 3, 4, 5, 6, 7, 8. Yes, sir. 1.
Right. So basically, the meaning behind H1 of x being 6 is that it's looking at that position 6.
Okay, this is the position.
Yeah, see, the diagram is clear, right? In that sense, the x is basically based on whatever value of x and h1, whatever function it is, hash function, it's getting a value of 6, which is mapping to the, let's say in this diagram, it's at the 4th position. In the answer, it's at 6th position.
Okay, understood, sir. Understood. Here, question here.
Okay.
Understood.
So I'm just seeing whether in the slides this was clearly mentioned somewhere. Let me just say, we'll see once. So we initialize the Bloom filter with zeros at every position. And whenever we are inserting for some x, so x is an input, we are setting that position to 1, you see.
To 1.
So H is telling which position to set 1. So H is always giving you a position because HIX is indexing the B array, right? And whenever you are doing lookup, HIX is telling you the position and it's checking whether the bit at that position is 0 or 1.
Okay.
So it's clearly a position, right? So I think now if you solve, you will get your, so why, let's complete this question. So H6 is, you are convinced that it's 1, H2 is also?
Everything is 1, sir. And I'm adding it, the output is 1, that may be present.
Yes,
fine.
May be present. Why not definitely present?
Fine. We cannot be sure, sir. I'm sure about it.
Exactly, because some other elements may have come and set those positions to 1. Right?
If the element is not in Bloom filter, if the element is not present, the output is not present, that means it is not present, it is sure.
Exactly.
But if the element is present, it may be present, it may not be present.
Perfect. Perfect. Yeah. You understand that very well. So good. Okay.
Sir, one more question, plus question number 8. Sir, using formula, which formula?
Good question. Let's see. If we want to design a Bloom filter for n elements with a false positive rate of 10%, then what is the length of bit vector and number of hash functions? So let's see what's there in the slide. So Bloom filter we have done. Yeah, so false positive analysis. We have m, which is the number of positions, and the n is the number of things, number of items to hash. So now the false positive formula in this slide is given as this. Okay. So
Which one is the formula?
no, let's see. So this is, you remember this as the like uniform formula that we had seen earlier, 1 by m,
That I understood.
right? So let's see, false positive analysis is telling us that the expected number of bits is 0, probability of lookup being present, and we can choose. Yeah, so for example, here it's telling us if we want 1% positive rate, we have 7 hash functions and total 10 n bits. So 1% means here you will, so in this formula, 1% is what? 1 by 100, right?
It's fine.
So log of 100 is, so basically log base 2 of this base.
So 1, 2. The answer is 1.
No, so, right.
Log of 100 is 2, sir.
Log of 100 base here, see in the denominator, there is log of 2, right?
Yes, sir.
So that is basically log of 100 base 2. Sorry.
So log of square, sir. Log square.
Yeah, sorry. Yeah, mistake. This is 7 hash functions and total 10 n bits. It is 10. So let's find the formula here. So minimize this thing. Why is it 7? 7 because if we set the choice to m is 7, 7 will be okay. I myself am a bit confused, so give me a minute.
It's okay, sir. Please, sir. Please take it.
Yeah, okay. So it's telling the expected number of 0 bits is this. The probability of lookup is 1 minus that expected value, and we have to choose to minimize it. So now what we do to minimize it, we take the log and derivative is set to 0. And so it is set to the log 2 by n. So optimal choice gives us 2 to the power m log 2 by n and false positive rate of delta. So this is the formula for getting m. So let's see. Let's say we have delta to be 1 by 100 as is here. So it's 2n by log square of 2. Right? Sorry, somebody has shown. Hi, Professor Anirudh.
Hi.
Hi. So Swarup was asking a few questions.
Sure. Please go ahead.
Currently he is asking about this formula. So if we want to design a Bloom filter of n elements with false positive rate of 10%, what is the length of the bit vector and the number of hash functions?
Right.
So we were looking at the formula here. So could you please explain this a bit, like why?
So first of all, right, see, we are only putting a restriction on the number of bits, right, on the number of bits that you can use, not on the number of hash functions. So Swarup, remember the analysis that was shown that says that if you fix the if you know the number of elements that you're going to insert, if you know the number of hash bits that you're allowed to use, basically the size of the that you're allowed to use, then there's an optimal number of hash functions, right?
Okay, sir.
Okay. So and then because there is no restriction on the number of hash functions, then obviously for the given m and n, you're going to use the optimal number of hash functions.
Yes, sir.
Right? For that m and n. That is the formula that's there. Okay? So now for this optimal rate, now we also know that if you use this optimal rate, if you use this right, then you get a particular rate, right, which is like 1 over to the power something. I mean, just plug this in into the error rate and you'll be able to get. So now that error rate is delta, right, which is the 10%.
This is the 1% is error rate. I know.
1%, not 10%, right? So now for the 1%,
10% is the question.
yeah. So for 1%, then I mean you're using the optimal m. I mean the optimal number of hash functions, and then the only other variable and is the number of hash bits, the m, because n is number of elements. Sorry, m is the m is the number of hash bits that you're allowed to use. Right?
Yes.
See, I mean, we are going at it stepwise. Saying that we know the number of elements that we're going to insert. We know that we want a 1% error rate, right?
Yes.
We have two things in our hands. We have the number of hash functions that we choose, and we know the number of and we can use so many size as the size of the Bloom filter. So of course, if you increase the size of the Bloom filter, it will the error rate will always decrease, right? But
Yeah, if we increase the size of the Bloom filter, error rate will also increase at one time.
No. The error rate will always decrease with increase in the size of the Bloom filter.
But sir, at some point it will increase. The error will increase.
No.
Because everything
You're
is
talking about the
1, 1, 1,
hash functions. You're talking about the number of hash functions. With the number of hash functions, it is not monotonic. But with the size of Bloom filter, it is also monotonically decreasing because there is always less and less collision. Right? But when you increase the size of when you increase the number of hash functions from 1 onwards, then at some point there is more collision, and then but because of the AND that we are doing at the end, right? I mean, the effect of more collisions is also nullified, but so there's a particular peak somewhere, and then it again increases. So it's basically decreasing, reaches a peak, and then starts to increase. That's kind of like the. So then that's the way to go about it. That first you say that that I know that if we fix m and n, then I know that that this is the optimal number of hash functions to use, and by plugging in the formula for the optimal number of hash functions, I know that for a given m and n, this is the best false positive rate I can get.
Okay.
And the best and you set the best false positive rate to be 1%, and you plug in the value of the number of elements that you use, and you automatically get that I definitely need to use this are the sizes of my group.
Understood, sir. But sir, can I ask you one thing?
Sure.
The way they have said that if we want 1% of FTR, we need 7 hash functions. But where they have explained this thing?
What is it? Can you repeat again? What is it?
If we want 1% false positive rate, we need 7 hash functions and 10 inputs. Okay, sir. This is an example. Okay. But professor has not explained this thing step by step. This is the formula and anything. The same question is over here also in the assignment. No explanation, nothing. Only just using formula. Which formula I use? Please use the formula.
This derivation was explained, right?
Huh?
This derivation was explained. How we arrived at this formula?
The derivation is not there, sir.
The derivation is there. Just trust me. I am the professor, so I give the lecture. So the derivation is there in the YouTube in NPTEL lectures. Entire derivation is there.
No, this log square derivation is there, sir. But how this formula is used in this question, that I am not understanding.
So you use this formula by saying that that you set delta to be equal to 1%, and you set n to be equal to the number of elements that you're inserting. That is all.
Sir, you do one thing, sir. Sir,
Yeah,
come to the question. Question number 8.
Okay. Can you just show the question number into?
Yeah.
Now, please tell me the formula and please tell me how to insert. I will be getting the value.
You have to think about the system, because it is not that this is not a plus b whole square and you plug in a and b and you get the number, right? So you have to kind of reason about it to say that look, that if you want, I mean, if I have the thinking step is the following, that if you have m and n, right, then there is an optimal false positive rate I can have for a given m and n. And that is by getting plugging in the optimal number of hash functions for this given m and n. Okay. So therefore, if n is given to me, the false positive rate is given to me, right? Therefore, the smallest number of bits that I can use is by plugging in this delta and the n in that formula.
Sir, I'm not getting, sir. I didn't get the answer.
So first you want the answer. So the answer is the following, right? The answer is you have. Okay. So now you have seen the for the possibility of 10%, what is the length of the bits and the number of hash functions required. Okay. So so now go back to the. Can we go back to the yeah, here. See, here what you are seeing is that the delta is 10%.
Yes, sir.
So plug in log 1 by delta and log 1 by 10%.
One second, I'm doing log 1 by delta, or 1 by 10 into n upon log square 2.
Yeah, exactly.
Okay.
So find out that is equal to that ratio, that m that you will get, that times n. I mean, n is still a variable. Is the size of the Bloom field.
But sir, how will you calculate this log 1 by 2 into n?
No, what do you mean by that? I don't understand.
Log of 1 by 10 into n, okay? Means n by 10, log of n by 10 upon log square 2.
It is not log of 1 by 2. It is log of 1 by, it is equal to log of 10. So delta is 10%. So delta is 0.1.
Delta is 10% of the 0.1. Okay.
So 1 by delta is 10. So you calculate log of 10.
Okay. Log of 10. Log of 10 is 1, sir?
Log of 10 is not 1. I mean, it depends on what is the basis. What is the base?
Yes.
If you take a base 10, then you also have to take the base 10 for the denominator.
Log 10 by 10.
Actually, this is base 2, I believe, because if I look at the formula above, this is base 2. To calculate log 10 to the base 2, then calculate.
Sir, how can I calculate log 10 to the power of base 2 when n is also involved with that?
No, how is n involved? N is not inside the log.
Acha.
It is only log 10.
Okay. Log 10. So, sir, what is that? Log 10 base 2, no?
Just to base,
Log 10 base 2.
Log 10 base 2.
One second, I'm trying finding the answer. Log 10 base 2. Sir, 3.32.
3.3. So 3.3. So that should be the coefficient of n.
Coefficient of n. Yeah, coefficient of n. Yes, sir.
And so you have to, I mean, because 3.32 is not an integer, so it is just round about that. And the k that you get, let me just bring up the slide.
Yes.
Okay, so I'm looking at a slide e to the power p equal to e to the power minus k by m. Okay, so I think we've been doing natural logs out here. Log of 1 by 10. Optimal choice is k equal to m log 2 by n. Yeah, okay. So in the previous slide, you see that the optimal k is given, right? The optimal k is m times. So these are all natural logs. I was sorry, I was not meaning m log 2 by n. Okay.
Okay.
And the 10% for this particular case you get delta, which is equal to 2 to the power minus m log 2 by n. Okay, and that
this is delta.
also
This
is
is delta.
10%. Yes, that is delta. That is 10%. Yes.
Delta equal to
the first line in this slide. 2 to the power minus m log 2 by n.
Okay. Okay.
So this is said to be 10%.
Okay. This delta.
Yeah. Okay. This is said to be 10%.
Okay.
And now solve for m. Solve for m in terms of small n.
Achha. So when type how sir?
How do you do this? You take logs of both sides.
Right. 10% is 1 by 100. 1 by 10 I will do, na?
10% is 1 by 10. Yes.
Yeah. 1.1 log 0.1 equal to minus m log 2 upon n log 2.
That is correct.
Okay, sir. Then n I'll put it over here. N.
Yes.
Log of 0.1 na. So log 1 minus 2. Sir, base is 2 na always.
I mean, you have done. I mean, you can take any base, but then you will have to decide what to do with the log 2. So if you take natural log, you will have a constant log 2 to the base. If you take a log of log base 2, then the log 2 of 2 log 2 base 2 will be equal to 1. So
Okay.
fix a base and work with it. But remember that this log log 2 that the log 2 expression that you have out here. I'm looking at what base we had there. The log 2 expression that is there, I believe that is
log square, sir. It's coming log square 2.
Yeah. I believe that is naturally I believe that. So the base for the log 2 is actually natural log. Is actually e.
Natural log.
Yeah. The base for the log 2 is actually e. I should have been clearer in the slides.
But sir, in the lecture they have said log 2, base 2.
Clarify that. So let's just go over the derivation again. So first we have in the previous slide we have have p equal to e to the power minus k n by m. So therefore the log of the false positive is log of 1 by p to the power k. Until this part it does not matter what log, k log.
Sir, one more question is there, sir. Sir, sir, log of 1, second thing, log of 1 minus p to the power of k log 1 minus k. Fine, okay, sir. Then you substitute the value of p over here, and you made m by n log p log 1 minus k. Is it okay, sir?
Yeah.
But sir, when I am doing, I am not getting this expression also. When I am doing the calculation.
Why are you not getting the expression? If you,
Sir, I don't know.
take the line above.
Yes.
Okay. So if you take the log of the both sides, on one side, see, this is where the natural log comes in. So take the natural log of p on the left hand side, and on the right hand side you get minus k n by m.
Okay.
Okay. So therefore k equal to, right, m by n,
Okay. Log 2.
natural log of p. And
Okay.
the minus also goes to that side. Okay.
Sir, I will try this. If I cannot understand, then I'll put it in the that window, that box.
Yes.
Sir, but what was about this question? So this will come in the paper. I know you will give.
Okay. So this is settled that this is natural log. This is natural log square 2. That is it. Okay, and now
That's fine.
okay, and now what is the problem?
Problem is that I'm not getting the answer also. That's 5 and
Let us calculate. What is natural log square of 2?
natural log square of 2. One second. Natural log square. Sir, 0.693.
Okay. So now what is calculate the square of that?
Acha. 0.693. On a 0.7 I can take, sir.
Sure.
Means 0.49.
Okay. And what is the numerator? Numerator is log 1 by delta.
Log 1 by delta. On a log 0.1.
Log of 0.1. Actually, that is a slight of a confusion, because that log of 0.1, that is log base 2. So
Yes.
you have to be more careful. Because this is 2 to the power minus some.
So can I ask one more question?
Yeah.
So from where you are teaching these things? Because I'm not getting in the internet also. You're giving the descriptions also, but I'm not getting this type of questions. Actually, I want to solve the exercises also for this, because sir, I actually now from the first week, second week, I was just okay, I will do it later on. Now I'm getting interested because it's getting tough for me. And when it is tough, I love it to do. I love to do.
Okay.
So from
So I
where
can
you getting that? Because I want to.
So we can, I mean, there's a bunch of references. I can send them. If you we can send the websites. I mean, there are very nice books on so first of all, look up a book by Graham Cormode on sketching.
Graham.
Let me just type out here.
Yes, sir.
Just type out the name of the book. So the book is free. The PDF is freely available. You can just search for this topic: sketch techniques or approximate query processing
Technique for.
Yeah, so I typed in the chat. You can
The
just
sketch technique.
sketch technique for approximate query processing.
Approximate Okay, sir. Right. And sir, one more thing. Can I ask you, sir?
Please.
May I have your email ID also, sir? If any queries, then I can go directly to you, sir. Please don't mind, sir.
Sure.
Please, sir. Because I am very much interested, sir.
I mean, you can get it just by Googling my name there, but it is my
Okay. Okay, sir. Anirban. That's good, sir.
Yeah.
Anirban. Sir, one more thing, sir. Can you go to class week 6, sir? Week 6?
Yeah, doing one sec.
Sir, one question is there. Week 6, let me show you the question. One second. I did all questions. I have a problem in only 2-3 questions, sir.
Acha.
See, data note, you know, sir, no notes are workers. You are asking about workers.
Which question number?
One second. I'm sorry. Question number 3. NAPA notifies workers only once at the end of task completion. So workers is the data notes you were telling about workers, huh?
See, a data node, out of the data node, not for this particular task, not every data node will have a worker, right? Because
Every
this
data node?
task, I mean, see, there might be 10,000 data nodes, right?
Yes, sir.
Now, out of these data nodes, this particular task maybe uses only 50 of them. So it has only worker tasks from only 50 of these nodes. That's what this is.
So, sir, mapper, why mapper notifies workers? Because under mapper node, data node is there, no?
No. See, mapper is a task. Data node is a node.
Under data node, that preserve data and
So
this
mapper is running on a data node.
Running on a data node.
Right? I mean, it's like, I mean, you're saying that my computer versus the LS task that I'm running. So your computer is not the LS task, right? Your computer, the LS task is running on your computer.
Sir, but sir, the way you have given the question, sir, I couldn't understand that. I've gone through a lot of theory, but I couldn't understand this question. Sir, only one mapper notifies workers only one. I think it notifies again and again the task is complete.
Mapper notifies workers only once. Then the task completion, true or false. What is the problem with this question?
Sir, the problem is that at the end of task completion, it notifies again and again, sir. Not only one. I want like that. Yes, sir. Yes, it's a false, sir.
So then I mean, you have a potential answer. So why do you think that you're not understanding the question?
Yes, sir. So, sir, what I'm saying, I'm not asking the answer, sir, but I'm discussing that. Okay, sir. Sir, কিছু মনে করবেন না, sir, please, sir.
No, of course, please. Good to have interest.
So, sir, mapper তো বারবার ওয়ার্কারের সাথে কথা করতে থাকে, একবার তো নয়।
So that is the point. So we are asking that is the statement that is being made, is the statement true or false?
Okay, understood, sir. And one more error is there. I think the question has an error, sir. Question number 9.
Question number 9. No, question number 9. Thank you. Okay. What is the error?
Error is, sir, yeah, it is there about matrix multiplication, but product of 2 matrices, but I am not getting any product over here. How is it saying product of 2 matrices, sir?
So columns, data ID and ID will be This is the mapper code.
Yes, sir. That I get.
Reducer was not. So we have not given the reducer for you.
The reducer is not there, sir.
No. Yes. I don't see anything. It's the product of 2 matrices.
But,
so this is not incorrect. We have given you only the mapper code. We have never told you that that we're giving you the entire map reduce code for the A also. For the
multiplication, product of 2 matrices.
For the matrix multiplication, right?
Okay.
Product will happen at the reducer.
Okay. Reducer will do
For
that.
that, you have to send the right data. You have to send the right data to the right reducer, right?
Okay.
And for that, you have to fill out this mapper.
Okay. Okay.
Missing information in this mapper.
Okay. ठीक है, sir. I will do this thing. And one more question. Question number 10, sir. Sir, reducer code count equal to 0, previous word equal to null. ठीक है, sir? छोटा सा क्वेश्चन है सर, मतलब बेसिक क्वेश्चन है, मुझे समझ नहीं आया एक्चुअली.
This is saying that which of these two options is the right fill in the blanks for this code.
I know, sir. I know. When I have taken a suppose a sentence, okay, sir. And from the mapper code, I suppose what is your name? What is one? Is one? Your is one. The name is one. Okay, sir. That is coming to reducer. It's fine because I'm not using combiner.
Okay.
The combiner won't work because I'm taking only a single sentence that doesn't have any duplicate element. Okay, sir. Now what is happening when I am taking the previous word equal to null, line dot instance dot std word count line dot string. Sir, when the line is already coming in string, then why is this line dot string? It's already coming in string, sir.
Word count. See what happens. See what happens. Yeah, I'll tell you what happens. Because in the reducer, when the key value pair comes, it comes as the tab separated format. The key tab value. That is why we are splitting the key from the value. In the reducer,
Okay, word with count.
Yeah, if you write MapReduce code, you will see that in the reducer you get the key value in the tab separated format.
Okay, okay. What? Suppose what? One. I'll get one. Is one. This I'll get, na?
Yeah. Now, if it is word tab one, you will get word equal to word and then count equal to one.
Now previous word is null, sir. It's okay. If previous word suppose at the first previous word is null. I'm doing dry run, sir. Please don't bite, huh? If previous word equal to word, it's not word, it's a null. If previous word not equal to null, it's a null, so it will come to count equal to 0.
Count, okay. Sure.
And previous word equal to word. Now the word becomes the previous word. Fine, sir. Then it's written article list dot append article ID. Where is this article ID come from?
Oh, okay.
Huh?
Yeah, article list. I think I think you're right. I think this article ID should not have been article ID.
It's okay. Leave that thing. Okay, fine. Leave it. I'm not interested in that. Okay, sir. Fine, sir. Previous word equal to word. Fine. Now I'm going again to that word count like that. If previous word equal to word, now previous word equal to previous word equal to word. Word है ये है तो previous word equal to word fine. तो क्या होगा count बढ़ जाएगा. Count equal to 1 हो जाएगा. Okay. Count equal to count plus 1 is fine, sir. Now previous word not equal to null. Previous word तो null नहीं है क्योंकि previous word equal to word हो चुका है. ठीक है सर. तो हम प्रिंट प्रीवियस वर्ड और काउंट को कर सकते हैं या प्रीवियस प्रिंट वर्ड और काउंट को करें. प्रीवियस वर्ड को भी तो कर सकते हैं सर. अच्छा सर, यहाँ पे फिर आर्टिकल लिस्ट और एपेंड गड़बड़ था ना सर.
आर्टिकल लिस्ट एंड आर्टिकल आईडी में कर. I think that just ignore that line. The rest of it is
okay. And sir, one more thing, sir. Actually, I have issues in week 1. Actually, sir, I didn't study properly. Now I have started studying. Please don't mind, sir. I know that I did the job of getting scolding.
This is your own study time. This is whatever time you can bring out. There's nothing for you to mind. That is the format of the
Can I say something? Sir?
Yeah.
Can I say something? Sir, I thought that this topic, this scalable data science is very easy thing. I know data science, I know deep learning, it's very easy. And when I came on the fourth thing, I understood that this is something different. I have to go inside it, how it is working. So I got interested, sir. So I'll be disturbing you, sir, for this questions.
Please go ahead. Please
please help me, sir. I want to do something good, sir. Please, sir.
Sure.
So that's all for today, sir.
Sure.
Okay. That's all. These are all the areas, sir. Nothing else, sir. Next time studying, sir. Okay, sir. Okay. Thank you, sir. Thanks a lot for helping me. Okay. Thanks. Bye.
Guys, unfortunately, I have to.
Okay. Thank you for
No.
helping out.
I think it was a good session. Thank you.
Yeah,
Thank
yes.
you for taking
Thank you, Shwaru.
Thank you. Bye. And sir, that question, the numerical question, sir, please help me, sir, in that.
Wait. I think professor left. Which one are you asking for in help?
Oh, that one. Oh, is that 5n by 4? That one with 2 questions.
This one. Bloom
Which
filter.
with 2? Oh,
Yeah.
yeah. How many that?
Oh, so
Bloom filter.
basically, okay. Just you are convinced that this is log based E, right? I mean, this is ln of 2. Okay.
I'm not convinced, sir.
Oh, you're not convinced. Okay, so what's happening
not
is, okay, so let's say this is correct. This comes from our previous slide. So the P is
Yes,
e to the power minus k n by m, right?
Yes, yes.
Now, if you take log on both sides and log is base 10, then this e would not vanish. There would have to be a e somewhere here,
Yes, sir.
right? The only way it can vanish if it is ln, log base t,
Yes, sir.
right? So this tells us that since this e is vanishing, so this will be ln of whatever. So ln of this e gives you minus. So basically e to the power something. Uska, if you take ln of that, then that will give you just this minus k n by m. Right. And you have ln p on this side.
Yes, sir.
So basically, if you like change sides, you will get this formula. So because this exponent is not existing anymore, that tells us that this we have assumed ln of p everywhere, wherever log is written.
Yes.
Okay. So after that, you know this is ln and this formula you have. Okay. So
Yes,
here, this false positive is what is being given in the question, right?
Yes, sir. Fine.
Now,
Understood,
what
sir.
you have to do that you have 4 options. You have values of m and n. You plug them in and you see which one gives you the false positive rate.
Sir, but m is not there, sir. M is not given in the question.
Where? It's
M is not
given, no?
given in that
In
question.
each of the options, it's given.
So I have to fit those options over there.
Yeah, what is the correct option? Length of bit vector is m. Number of hash functions is given here. And then you have to set them and see. Try once. I think you can do it with this.
Okay,
Otherwise, put in the
I
discussion.
will be coming in the discussion.
Yeah, yes. I think you will put it. You just have to put it and see what gives you, because you have to use a calculator. You have to do it once and check what gives you the false positive rate.
Okay, sir. I'll use it.
Okay.
I'll try, sir. If any error, I'll come over there.
Yes,
Thank you,
sure,
sir.
definitely.
Okay. Thank you, sir. Thank you.
Okay.
Thank you.
Thank you.
Okay. Bye. Bye. Good night. Good night. Thank you.
Good night. Good. Thanks. Hi, so we are done for today. I think you can leave. I'm stopping the recording now.